Our understanding of the universe is a house of cards, built high upon a scaffold of pre-existing theories and tentative one-off results. And so, most experiments in modern theoretical cosmology are not as they were in the early days of physics. They are not voyages of blind discovery, but rather finely tuned confirmations of predictions already made, of results already hinted. The Higgs boson was first predicted in 1964 and finally confirmed in 2013, just as expected. But what scientists really hope for are surprises. A result that topples the house of cards and builds a new one in its place, or totally cements the linkages and proves the theories once and for all. And so, in early 2021, in a laboratory near Chicago, 200 virtually assembled scientists shared a gasp of excitement. Had they found just such a result? The experiment and analysis were the culmination of more than 60 years' work, involving physicists from 35 institutions in 7 countries worldwide. And yet, until an envelope was opened in Batavia, Illinois, and a secretive key typed into a computer, not one of them really knew what they had accomplished. This elaborate cloak-and-dagger approach to experimental physics, perhaps more suited to a star-studded film festival, was necessary to avoid any one of the hundreds of collaborators inadvertently biasing their findings towards the desired outcome. This latest experiment at Fermilab was concerned with the behavior of muons. These exotic particles are the heavier cousins of electrons and exist only for a couple of microseconds before decaying into something else. Like an electron, a muon has electric charge and behaves like a spinning magnet. But that spin wobbles when muons move through a magnetic field. So, using the incredibly complex mathematical tools of quantum mechanics and the so-called standard model of particle physics, scientists have predicted exactly how much the muons should wobble. This theoretical prediction represents the sum of what we think we know about how the universe works. And the elaborate experiment at Fermilab was designed to test this theory, to find out if we are right. To do this, researchers spent 4 years installing and calibrating a huge C-shaped magnet, some 15 meters in diameter, with an impeccably uniform magnetic field. For more than a year, they spun muons around the magnet and measured their wobble. And sitting at the controls of this machine, waiting for the beam to fire, our researchers would have had plenty of time to contemplate the theoretical house of cards on which their predictions were built. All matter in the universe, from the muons inside the magnet to the researchers themselves, is subject to 4 fundamental, irreducible forces. Gravity keeps the scientist pinned to the seat of her chair, keeps the huge magnet stuck to the surface of the Earth, and keeps the Earth in orbit around the Sun. Electromagnetism provides the invisible pull within the gigantic magnet, but it does more than that. It is responsible for the electric currents that flow through the equipment's controls, and for the electrical impulses that spark through the scientist's body to keep her heart beating and her neurons firing, shrinking down further to the scale of atoms themselves. The strong nuclear force grips the particles together in every atomic nucleus, holding them fast despite the repulsion of their like charges. Without this force, not a single atom in her body, the room, or the entire universe could exist. They would simply fly apart in a cloud of unconnected quarks. And yet, in a few thousand atoms inside the scientist's body, the weak nuclear force is driving such elemental destruction. The 4th fundamental force is the agent of radioactive decay, which sees atomic nuclei, like the potassium-40 inside our cells, cracked open and transformed. Together, the actions of the 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are enough to describe every single phenomenon in the universe today, except, it seems, the wobble of muons. The revelation unlocked with the opening of Fermilab's envelope was that the intricate predictions built on these 4 forces for the muons were not, in fact, correct. Muons wobble more than they should, and the results showed with unprecedented precision that there is likely to be something else at play, a 5th force, as yet undiscovered. There is still much work to be done to understand the significance of this curious muon wobble, but it gives us cause to re-examine what we think we know about the four fundamental forces that we are aware of. Our understanding of them, too, the result of centuries of scientific revelation. Why are they fundamental to the universe, and are they really as distinct as we think? How did the directionless quantum foam at the beginning of our universe give birth to these fundamental natural laws? Extending our house of cards back to the very birth of the cosmos, we find that things looked very different for a brief moment of grand unification. The existence of invisible forces at play in our universe has been recognized for thousands of years, and mankind has strived to understand and harness them for almost as long. Lodestones, pieces of naturally magnetic rock, were treasured and used for divination by the Chinese since the 2nd century. Ancient Egyptians were wary of shocks from electric fish, and early philosophers experimented with static electricity with rods of amber rubbed on cat's fur. But these strange phenomena graduated from mere curiosities in the 17th and 18th centuries, as the scientific revolution forced them to yield their secrets. They became the subject of rigorous study by scholars and statesmen alike. Founding father Benjamin Franklin reputedly sold all his possessions in order to fund his research into electricity. It is ironic, therefore, that his most famous experiment required little more than a kite, a key, and a thunderstorm to prove that lightning was electric in nature. The summer of 1864 was a hot, dry swelter. It had barely rained since April, and in the offices of King's College London, the air hung heavily in the dim wood-paneled rooms. Desperate for some relief from the baking heat, James Clerk Maxwell staggered to the window and heaved the sash open, letting in the clamor of the streets below. The air had a sharp and slightly sweet smell to it, one that Maxwell knew heralded a coming lightning storm, and which we today would recognize as the distinct smell of ozone. He hurried back from the window, eager to finish his observations before the coming light show. A trickle of water poured from a pitcher above his head. For the last time that day, Maxwell rubbed a glass rod back and forth across his woolen waistcoat, long since discarded, and held it up close to the steady stream. As he expected, the water bent toward the rod, tugged subtly by an invisible force. A nudge too far, and the water reached the rod itself. This seemingly magical manipulation of the watery stream was the work of static electricity, the attraction of like electrical charges on the rod and in the water itself. No one knew the potential of electromagnetism better than Maxwell. As a child prodigy, he'd spent his teenage years considering the mysteries of mathematics and had now turned his considerable intellect to understanding the nature of the universe. And so, building on thousands of years of accumulated knowledge, James Clerk Maxwell was the first to visualize the seemingly magical action of non-contact forces as the product of an invisible field, like a three-dimensional web radiating out from its source. Not only that, but Maxwell saw that since electricity could produce magnetism, and vice versa, then the fields for those two forces could, in essence, be combined into one great electromagnetic field. As waves propagated through this three-dimensional web, they carried energy undiminished from one location to another. Visible light is one such electromagnetic wave. Maxwell's unique perception of electromagnetism as a unification of electricity, magnetism, and optics paved the way for a revolution in our understanding of physics. As he opened the window to his stifling office, he unknowingly let in a breath of fresh understanding for all who followed him, laying down a foundational ace in the cosmological house of cards. His equations allowed electromagnetic waves to be produced and studied in the laboratory, leading to the discovery of radio waves some quarter of a century later, and providing a framework for visualizing the cosmos in an entirely new way through the action of fields. And so it was that in the early 20th century, Albert Einstein had Maxwell's fields in mind as he rewrote the mathematics for gravity, giving rise to the fabric of space-time, an immense field that is curved and distorted by massive objects like stars, planets and black holes, like the endlessly propagating waves of electromagnetism, gravity also acts over cosmic distances. And all is caught in its grip to varying degrees. Although our day-to-day lives are ruled by the gravity of the Earth and the Sun, the force of gravity isn't actually that strong. In order to produce measurable gravitational effects, one must accumulate huge amounts of mass. Like the 6 million billion kilograms of the planet Earth, the curvature of space-time produced by a human body or an apple is so small as to be almost unmeasurable. Instead, on the smallest scales, the microcosmos is ruled by another, the strong nuclear force. In contrast to the far-reaching fields of electromagnetism and gravity, the strong force only extends its reach a minuscule distance, no more than the diameter of a proton. But despite this small sphere of influence, the strong force truly lives up to its name. It is this that binds together quarks to make the protons and neutrons at the heart of every atom, and its residual effects are powerful enough to hold protons together despite the fundamental repulsion of their like positive charges. Finally, with an even smaller sphere of influence and a potency less than all but gravity, the weak nuclear force may seem barely worth considering. And yet, its effects are ones we rely on for our very existence. The weak force is responsible for changing the flavor of the quarks that make up protons and neutrons, transforming one into another to build or destroy atomic nuclei. These changes, when they occur inside the hearts of stars, fuel the fusion that keeps them burning and stabilizes the assembly of heavy elements. Thus, we ultimately have the diminutive weak force to thank for the life-giving heat from the sun and for the very building blocks of our planetary home. Between them, the four fundamental forces appear to govern every known phenomenon in the modern universe. Understanding the fields of these four forces has helped modern physicists to grasp, model, and predict the cosmos with spectacular precision. But to answer the question of what these forces really are and how and when they came to be baked into our early universe, we must step further through the force field, into the baffling world of virtual particles. Cornell University nestles close to the southern shore of Cayuga Lake in upstate New York. On late autumn evenings, a gentle breeze blows down towards the lake to blow delicate ripples across the water's surface. In the late 1940s, Richard Feynman, then associate professor of physics at Cornell, sits in quiet contemplation at the shore. He is watching the water dance to the wind's choreography, and he is thinking about quantum electrodynamics. The patterns on the water's surface change from moment to moment, driven by the invisible forces of the wind. Feynman imagines a wind field, much like the electromagnetic fields of his research, radiating out across the lake to create those tiny rippling waves. With enough information, he could imagine reconstructing the wind's field, relating it mathematically to its source atop the hillside. But to truly understand the wind, the large-scale field is not enough. He would need to know about the particles of air that carried the wind's power, how they moved, how they interacted with one another and with the water of the lake. The wind's field relied ultimately on the particles that carried it. Could the electromagnetic field be similarly reduced? Feynman was riding the growing wave of the quantum revolution. For the last 20 years, interrupted somewhat by World War II, theoretical physicists had begun to comprehend the universe on a tiny particulate scale, recognizing that light waves could be quantized into minute parcels of energy known as photons. But as James Clerk Maxwell had shown some 80 years previously, light is also a wave, a manifestation of the electromagnetic field that permeates the universe. How could these two differing viewpoints be reconciled? Feynman provided a mathematical solution in the form of quantum electrodynamics, quantizing the electromagnetic field and defining the interactions of particles that deliver this far-reaching force and its many effects. The messenger of electromagnetism, he determined, was indeed the photon. But photons are not physical, tangible particles like the air molecules that make up the wind. They are virtual messengers, quantized parcels of energy that don't interact with one another, but nevertheless can be exchanged to alter the properties of real matter, producing the different effects of the electromagnetic force. Free photons that are emitted and not exchanged become visible light and other forms of radiation. And bizarrely, according to the strange tenets of quantum dynamics, these virtual photons can briefly pop into and out of existence even when there is nothing else around, for example, inside a true vacuum. Normally, their fleeting existence goes unnoticed, but in 1948, Dutch physicist Hendrik Casimir found that when two mirrors were placed facing each other in a true vacuum, they would be mysteriously attracted to one another. The only agent of force could be these virtual photons. He reasoned that more of the messenger particles could exist outside the mirrored plates than between them, and the resulting pressure difference was enough to force them ever so slightly together. The phenomenon is known as the Casimir effect, and it is an elegant demonstration of the energy contained within all vacuums throughout the universe, now and since its creation. Like Maxwell before him, Feynman's new treatment of the electromagnetic force once again revolutionized theoretical physics. Recognizing that one of the fundamental forces of the universe could be so quantized, physicists spent the following decades following in Feynman's theoretical footsteps and seeking the virtual messengers of the other cosmic force fields. The strong force was the next to reveal its secrets. Probably owing to its strength, allowing it to be studied in laboratories as soon as sufficiently precise instruments could be built. The study of quantum chromodynamics is therefore concerned with the agents of this powerful yet limited force. The virtual messenger in this case is the gluon, so named for its ability to glue quarks together to form protons and neutrons. But the message that these gluons carry is more complex than the simple energy exchange of photons. Nevertheless, through theoretical and mathematical attrition, photons and gluons found a place within a modern framework of particle physics known as the Standard Model. Under experimental scrutiny, even the weak force, with its tiny reach and feeble powers, has yielded its own virtual messenger particles, called W and Z bosons. And they are different again from gluons and photons. They are massive, with roughly 100 times the mass of an entire proton, making them heavier than entire ion atoms. Compared to photons with zero mass, these massive messengers are confined by their own inertia. To date, only the gravitational force evades quantization. Theoreticians have predicted the existence of a virtual messenger with zero mass, called graviton. But there are fundamental incompatibilities between the quantum standard model and our other framework for understanding gravity: general relativity. Gravity is 1,000,000 billion times weaker than the weak force, making it impossible to probe with the kind of instruments we can build now or in the foreseeable future. But even without gravity, the standard model has gone a long way to probing the fundamental forces on their smallest scales. And yet, frustratingly, the solutions to these natural puzzles seem far from standard. All of the virtual messengers that we have discovered behave in their own unique ways and have their own unique properties that render the fundamental forces just that, fundamental and irreducible. And yet, remarkably and somewhat counterintuitively, physics today is painting a more consolidated picture in which these irreducible forces are simply facets of a single unified whole, one which had its origins in the earliest moments of the cosmos. Professor Salam stepped forward to receive his Nobel Prize on the 10th of December 1979. He allowed himself a small smile, reflecting a brief surge of pride within. He was a humble, private, and modest man who seldom wasted his energy on self-reflection, preferring instead the relentless pursuit of knowledge. Salam's genius had manifested at an early age, and he pursued his academic career in Lahore, in Pakistan, and in Cambridge and London in the UK. While working on his doctoral thesis, he managed to solve in 6 months a mathematical physics problem that had vexed the great Richard Feynman for his entire career. His Nobel Prize was shared with 2 other American physicists, Sheldon Glashow and Steven Weinberg, for a solution that the three of them had been working on for the preceding 2 decades. They had proven, in yet another paradigm-blasting moment for physics, that 2 of the 3 apparently irreducible fundamental forces of the universe could in fact be united into one. The weak force, with its minuscule range and diminutive power, delivered by massive virtual messengers, could not seem more different from the electromagnetic force's infinite reach, a strength some 10 million times greater, and a massless photon messenger. Yet they showed that electromagnetism is an intrinsic and necessary component of the weak force, and that these 2 superficially different fundamental forces are merely manifestations of one, the so-called electroweak force. Salam, Glashow, and Weinberg's theory was yet another turning point for understanding the physics of the universe. Just as the atom was once thought to be the fundamental, indivisible building block of matter, only to be split time and time again by advances in experimental physics, so 2 of the irreconcilable fundamental forces of nature had been unexpectedly united. But in the physical world, it would take extremely high energies, equivalent to a temperature of about a quadrillion degrees Celsius, for the electromagnetic and weak forces to be truly united, to act as one. Modern physicist Alex Filippenko has visualized this as a coin spun across a table. When it is spinning fast, it is hard to distinguish one side from another. It appears symmetric and unified like the weak force. But as it runs out of energy and settles, that unification is broken to reveal 2 distinct sides, heads and tails. Or in this case, weak and electromagnetic forces. Buoyed and encouraged by this remarkable discovery, Abdus Salam, along with an enthusiastic new crop of theoretical and experimental physicists, turned to the next possible unification, that of the strong force with the electro-weak. This so-called grand unification theory would seek to describe 3 of the 4 fundamental forces within the same framework, for now gravity, which evades quantization altogether, is a challenge too far, but even grand unification is hard to prove. Theoretical physics has predicted that at sufficiently high energy, the distinct virtual messengers, photons, gluons, and wavons, bosons, would cease to exist and be replaced by a single unified particle known as an X-boson. Measurements of the 3 forces at increasingly high temperature have revealed changes in the relative strengths of these forces. The strong force gets weaker, the weak force gets stronger. We might imagine that by turning up the dial, by cranking the energy up even further, they will eventually converge and become one. But in reality, there is no dial. We cannot go any further. The predicted energies necessary for this grand unification are some million times greater than for the electroweak force. Such energies are simply beyond our reach on Earth or anywhere else in the universe today. Even if we somehow harness the powerful blast wave of a supernova, or the jets from a black hole or neutron star, these would still be about 1 billion times too feeble. And yet there was a time when such blisteringly high energy reigns supreme across the universe. For a few fractions of a second, moments after the Big Bang, the eponymous Grand Unification epoch saw 3 forces combined into one, with truly bizarre consequence. Near the cosmopolitan Swiss city of Geneva, an engineer turns the valve on a canister of compressed hydrogen, allowing the atoms to stream out to high pressure. The atoms flow through an electric field, which strips them of their electrons, leaving only naked protons to fill the adjoining airless pipe. From there, the positively charged protons are subjected to alternating electric fields that pull them along the pipe, accelerating them to ever greater speeds. At points, radio waves are injected to give them an additional push, and strong magnets arranged around the pipe bend the beam of protons around an endless curve. The proton beam is spun around 4 successive rings of increasing diameter and length, building speed and energy with each pass. At last, the beam is split in 2 and sent in opposite directions around a 27-kilometer-long ring, until, with pinpoint precision, 2 fated protons collide in a shower of subatomic particles. This is CERN's Large Hadron Collider, the most advanced and powerful particle accelerator in the world. The energy of these proton collisions is on the order of 10,000 giga-electron volts, corresponding to a temperature of about 100,000 trillion degrees Celsius. This is the greatest energy we have created in experiments on Earth. But it is still a very long way from probing the energies of the early universe. Trace our expanding cosmos back through time, and all of the matter and energy within becomes denser, more tightly packed, and by extension hotter and more energetic. At the unfathomably small scales that reign just after the Big Bang, physicists predict that the entire universe had an energy of 10 to the power of 16 giga-electron volts. That's 10 followed by 16 zeros, equivalent to a temperature of 100,000 trillion degrees. It is some trillion times higher than the Large Hadron Collider has ever managed, or indeed ever will. There is no experiment that can tell us how the universe behaved under such extreme conditions. But the work of Maxwell, Feynman, and Salam and his colleagues has helped us imagine how the four fundamental forces worked during these earliest moments. For 1 unit of Planck time, a 10 million trillion trillionth of a second after the birth of the universe in the Big Bang, utter weirdness ruled. Gravity, as we know it, did not exist, was unable to exist in the excruciatingly small embryonic universe. This was the Planck era, defined by a seething quantum foam composed of micro-black holes and wormholes popping into and out of existence without any recourse to logic or causality. But by the end of this minute fragment of time, the baby universe had expanded and cooled enough for the enigmatic force of gravity, such as we understand it, to manifest. Gravity may now be distinct, but the temperature and energy of this hypercompactified universe is still high enough for the three other forces, strong, weak, and electromagnetic, to be combined into one, the so-called electronuclear superforce. During this grand unification epoch, the entire cosmos is still less than the size of a single quark and is filled with a sea of photons, which spontaneously transform into pairs of matter and antimatter, creating the smallest particles of physical stuff in the universe. They are the quarks, the building blocks of protons, and leptons like electrons and muons. But these first particles do not stick around for long. The extremely high energies that prevail mean that these particles are just as likely to decay back into photons. So over time, the physical component of the cosmos doesn't truly grow even for the brief time that they exist. The combination of the three fundamental forces means that these matter and antimatter particles don't behave in any way that we might expect. Instead, physicists think that the X-boson messengers of the electron-nuclear force may have driven the conversion of quarks into leptons, of matter into antimatter, and vice versa. This primordial game of cosmic tag is the ultimate magic trick. Just a tap from an X-boson magic wand is enough to turn the white rabbit into a bunch of flowers, or back the other way. When the forces that define our natural laws are combined, the universe is a lawless freefall of virtual and real matter and antimatter, quarks and leptons. No one component dominates over the others, and the composition of the universe dynamically shifts from one tiny moment to the next. The universe continues to expand and cool throughout the grand unification epoch. Yet, for all the magnificence of its name, this great epoch is over in the blink of a figurative eye. Almost a trillionth of a second after it started, the grand unification epoch is brought crashing to an end. The temperature of the cosmos is now a mere 1,000 trillion degrees, cool enough and with energies low enough for the strong force to emerge as a fundamental force in its own right. And so the end of one great age marks the beginning of another. This is the electric weak epoch, ruled now by gravity, the strong force, and the unified electric weak force, desperation. The emergence of the strong force, the temperatures during this time were still so high, and the fleeting quarks so energetic that this newborn force had little chance to act. The quarks remained free and unbound, and familiar protons and neutrons were an unstable rarity. And yet, there was a change in the overall balance of the cosmos. With the loss of the super-unified electron-nuclear force, the messenger particles of that force also disappear. The X bosons decay themselves into an assortment of matter and antimatter, quarks and leptons. The splitting of the great force for the first time seeds the universe with stuff that is predicated a rapid cosmic inflation that characterized the universe's next great era. Thanks to the huge differences in unification energies across the three forces, the electroweak epoch lasted a veritable eon compared to the time of grand unification. After nearly human billionths of a second, the universe had inflated exponentially, had seen the decisive creation of matter from energy, and had cooled to just 3 quadrillion degrees. And only at this point, when particle energies dropped to about 1,000 giga-electron volts, did the weak force and the electromagnetic force become distinct from one another. The 4 fundamental forces of our modern universe finally began to function as separate entities. This picture of a unified beginning has been the culmination of all modern thinking in experimental particle physics and early universe cosmology, backed up by more than 1,100 years of revelations about the fundamental laws that govern the universe. How then do the recent tantalizing hints of a potential 5th force fit in? Some have suggested that the finding undermines the carefully constructed house of cards on which our understanding of particle physics relies. Others, more optimistically, hope that the tiny anomalous wobble of muons could be the key to unlocking some of the more enduring mysteries of the modern universe. Could the 5th force be somehow linked to the dark matter that holds rotating galaxies together against their whirlwind spin? Could it be connected with the dark energy, whose effects are only just beginning to be felt as the cosmos's expansion accelerates? Time and work will tell. The Muon experiment continues through 2021, with several more runs through Fermilab's gigantic magnet, hoping to narrow down the precision of the measurements even more. The 200 collaborators are cautious in claiming a discovery just yet. In their preliminary results, there could be a 1 in 40,000 chance that the muon wobble is a random chance event. So before they're sure a 5th paradigm-blasting force is really there, the scientists are hoping to reduce that chance to just 1 in 3.5 million. If and when that happens, we will be soon looking to the future, Feynman, Salam, or Maxwell, for the next revelation in unified physics. You've been watching The Amazing Universe. Don't forget to like and subscribe, and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.